Hello everyone, I am Aaryan Awadh. I am a summer research intern at Maritime Research Center and I am currently working on developing an enhanced collision avoidance system to detect and prevent ship collisions. Now, the main goal of this project is to develop an automated system for detecting collision probabilities based on AI models using satellite data. Now, first, let us look at the need for collision avoidance. Now, as we all know, the maritime transport serves as a huge metric in determining the overall progress of the world in terms of both GDP and overall development. Now, owing to this fact, the number of ships in the oceans have been steadily increasing at the rate of almost 10% every year. And this has gotten to the point where in the last 40 years, the number of ships have basically gone from to 4 to 5 times of what they were at the time before. Now, owing to this huge increase in maritime traffic, there has also been a particular problem of increased risk of accidents and particularly collisions. Now, if we look at the data for a particular region, in 2021, almost 31% of all the shipping incidents reported in Canada were due to ship collisions. Now, the thing with ship collisions is that these cause a lot of economic damage with all with predictions that almost $2 billion of losses were incurred only due to ship collisions, and even apart from the financial losses, there are severe environmental damage to the marine life in the entire area. Now, the current methods of collision avoidance basically use methods that are either incapable or based on very old regulations. Some of them are radar and remote sensing, and the problem with these kinds of methods is that they only use sensors that are present on inside of the ship, and therefore they lack the awareness of the entire wide region where various of the ships can be present, especially in areas of very high traffic density. And a lot of the methods are also based on the call rate compliances, but the call rate compliances were developed in 1972s and they are no more suitable for the current maritime traffic since they use very vague terminologies like early, large, wide, clear actions are recommended for effective collision avoidances. There are also other methods, but they simply recommend just changing the speed of the vehicle, and also they inform the people on the ship at the very last moment, which can lead to unexpected situations and not very accurate collision detection. Now, the new methodology that I have proposed during my work was to integrate both AIS and satellite for tracking the ships. And after combining the data, we will use a combination of multiple AI modules for the purpose of detection. Now, since the last few years, the satellite data has become readily available, and therefore it has become almost imperative to use them for our applications as it is a very reliable source of information. And the development in AI models in the last few years have also unlocked new helps in the possibilities of automation, and they can enable us to monitor regions that are almost impossible to manage manually or by humans alone. So the new system that I have developed for detecting the ship collision index basically uses two sources of data. First is the satellite image data, and the second is the AIS data, that stands for Automatic Information System, that is transmitted from every ship that is on the ocean. So first, from the image data, we use the YOLO V9 object detection model to detect the ships present in the entire region of our surveillance. And after the ships have been detected, we match them with the AIS data using another classification aided model, especially the Rust Boost model, to identify the exact identity of the ship detected in the image. Now, after the identity of the ship has detected, and we have also AIS information about the various velocities, locations, and the speed and the course over ground of the ship, we can use all this information to accurately and very precisely predict a high confidence collision risk index, which is based on the DS information theory. Now, the thing with this collision risk index is since it is not only dependent on the distance as elected by the previous methods and lot of multitude of other factors, the final output, that is the risk index that is given using this method, is much more accurate and reliable than all the other methods that are currently being used. Now, for this, the different sources of data are mainly the AIS data and the SAR data. And the reasons for choosing the SAR image data specifically from the Sentinel-1 satellite mission was that SAR stands for synthetic aperture radio data, and this data does not use optical sensors, and hence it is not prone to disturbances from weathers and like cloudy weather or severe turbulences. It can detect and provide information in almost all weather conditions as long as the satellite mission is running. And for the training purpose, the images that were used were uh, kept at 1 meter resolution for the developing the entire system, but the the model I've used was also trained on 0.5 meter and 3 meter image resolutions to ensure consistency in case the output of the satellite changes. Now, here are all the new models that I have used in the project and the implementation. So, as discussed above, for detecting the images of the ship from the SAR images, I have used the state-of-the-art YOLO VNet detection model. Now, the reason for using this model is this model already comes pre-trained with a lots of weights and parameters on a large data set of real-world objects. So, you, molding it for our use case becomes relatively simple as it only requires a small data set of 3 to 4,000 SAR images to be giving very accurate results on our specific use task. For the AIS and SAR association, a Rust boost ensemble method was used that uses various decision trees for the association purpose, and almost 90% of the ships that were present in the SAR images were accurately identified with their MMSI codes using this model. Now, the final risk collision index was also used, calculated using a machine learning based CRI estimation model. And while it could have been used by a simple DS evidential theory based quantitative model, the reason for using the machine learning model was that the DS model is very comprehensive and uses a lot of calculation and inputs to give the final results. And hence, since it's a quantitative model, it can easily be modeled using any tree-based model while having a significantly lesser computation cost. So I also trained a model for this purpose, which achieved a validation accuracy of 97% that ensured its ability to replace the current method very confidently. Now, while developing the entire system, it was also taken care of that each model that is used was developed with the least amount of parameters on the smallest precision so that to make the entire pipeline computationally feasible and as light as possible so that it can be used for real world streaming and not just for research purposes. Now, as for the final results of the research, the model that was used for the ship detection could accurately detect 87.54% of the ships present in the image with almost pinpoint accuracy, and the rest 13% of the images were detected with a slight offset in their positional locations. But regarding the entire system, even the slight offsets in the positions didn't contribute much to the final collision risk index. And also, since the model used was very lightweight and low in parameters, the FPS of the entire system was 23.53, ensuring that around 30 images can be processed each second, and the indexes of each ship present can be updated 30 times per second to ensure its use in real-time applications. And even the model that was used for the AIS and SAR association gave a 90% confidence boost to all the identification numbers of the ship and the collision risk indices. Now, apart from this goal of the research, while doing it, I also came across another work that could be used using this AIS and SAR association, that is detection of dark sea vessels. And while that was not the main motive of the research work, the model that is developed here could also prove to be of major importance of detecting dark ship vessels that turn off their AIS data during illegal activities. With this, I would like to conclude my presentation. Thank you, everyone.